If you're like most people, after you get maybe a few weeks into a linear algebra course, you start to cringe every time you're asked to solve a system of equations. It starts to become kind of tedious, and you're sick of always putting things in row-reduced echelon form. And so, it's about time that we enter the matrix. Let's start with some definitions. An m by n matrix is a rectangular array of numbers with m rows and n columns, and each number is called an entry. And so, if we discuss matrix M, and we're talking about something in the 2, 5 position, that means it's in row 2 and it's in column 5. A matrix is square when m is equal to n. When we discussed the system that you saw in example 14, with all these x's and y's and z's, you can model it with a matrix without any of the variables. It's assumed that the first column is going to hold the coefficients of all the x's, and the second column is going to hold the coefficients of all the y's, and the third column is going to hold the coefficients of all the z's. And this is considered a square matrix, 3 rows and 3 columns. And that's done on purpose because the system that we're talking about there has 3 equations and 3 unknowns. You might ask, well, what about the right-hand side? What about 4, 0, 4? They don't show up in the matrix at all. And there's good reason for that. We began talking in the last video about the power of using a homogeneous system. And in the homogeneous system, the right-hand sides are all zeros anyway. However, if you did want to include the right-hand side, then you would use an augmented matrix in which the right-hand sides were shown just to the right of a vertical line. The vertical line, of course, represents the equal sign. Just so you can see how much faster it is to solve a system of equations using the augmented matrix form, let's have a race. Ready? Get set, go. Okay, that was fun. As you can see, writing all those x's and y's and z's is a little bit unnecessary. However, perhaps the more important thing to consider is once we switch from equations with variables to a matrix, we start to understand a lot more about our systems of equations. And eventually, we start to understand about matrices as more than just an organizational tool. Let's start with a definition. A square matrix is called non-singular if its rows are all linearly independent. That is, no row can be formed by taking a linear combination of the other rows. Otherwise, the matrix is called singular. Let's look at a few examples in order to help us understand. First, let's consider the matrix 1, 2, 3, 4, 5, 6. I don't have to think too much in order to classify this matrix as singular or non-singular. I can just glance at it and say, hey, this must be singular. And the reason for that is a non-singular matrix is by definition square. If the matrix is not square, and 2 by 3 is not a square, then the matrix is automatically singular. However, there's another way to think about this. The rows of this matrix are 1, 2, 3, 4, and 5, 6. And the definition of a non-singular matrix says there's no way to create any of those rows by linear combinations of the other rows. So that's saying that there's no way to put, say, some amount of the blue row, 1, 2, together with some amount of the yellow row, 3, 4, in order to produce the green row, right? It's saying it's impossible to do linear combinations of 3, 4 and 1, 2 in order to produce 5, 6. Well, that just isn't true, because I can clearly see that if I double 3, 4, I'll get 6, 8. And if I take 6, 8 and subtract 1 from the 6 and 2 from the 8, well then I'm surely going to get 5, 6. And thinking about this algebraically, sort of reorganizing it, what that really means is I'm taking 2, 3, 4s, I'm subtracting 1, 1, 2, and then I'm subtracting one more, 5, 6 from it, and what I'm actually getting is zeros, a row of zeros, right? A matrix is going to be automatically called singular, even if it's square, if you can somehow do linear combinations, your normal row reduction, and get a row of zeros. Let's look at another example. Let's say we have the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Same question. Is this matrix singular or non-singular? Well, we actually have to think about this one, right? Because if it's square, it could be non-singular, but it must fit this criteria that there's no way to form a row, say 7, 8, 9, through linear combinations of the other rows. Well, let's just think about it. An easy way of answering this question is using row reduction. If we take the matrix and put it in row-reduced echelon form, here's what we find out. First of all, we notice this row of zeros at the bottom. This tells us the row 7, 8, 9 was redundant. What's more is we see the exact prescription that you should use to combine the first row and the second row in order to produce the third row. If you take 2, 4, 5, 6s, you get 8, 10, 12. And if you subtract 1, 1, 2, 3 from 8, 10, 12, you've got 7, 8, 9, which tells us that this matrix, even though it's square, is indeed singular. In this example, you're presented with 9 different matrices of various sizes, and you're asked to classify these matrices as singular or non-singular. Pause the video and see if you can do it. First, let's look at the answers and then explain. First, we'll look at the 2 by 2 matrices along the top. This matrix right here is non-singular. The one next to it is also non-singular. The third one in this row is singular. Why is that? Well, the third matrix here, upon row reduction, would be 1, 2, 0, 0. And that's because if I take the first row and multiply it by 3, 1, 2 multiplied by 3 creates 3, 6. And thus it's singular, even though it's square. In the second set of matrices, I've got a singular matrix right here. And this is because if I just focus in on what's happening down here, I see the same problem that I saw in this matrix. And so if I take 2 row 2s, I'll end up with row 3. This one in the middle is also singular. And this is easy to spot because I can see that if I take the first row and add the second row, I'll get the third row. Meanwhile, the last one in the middle here is non-singular. The easiest way to see that this is non-singular is if you row reduce it, you will get 1, 0, 0, 0, 1, 0, 0, 0, 1. And this is a very special matrix that we call the identity matrix. Anytime you row reduce a square matrix and get the identity, it tells you that it's automatically non-singular. You don't have a row of zeros in the identity matrix. The last three are all pretty obviously singular because they are non-square. In this example, we're presented with two different matrices, matrix 1 and matrix 2. And these matrices have some variables in them. And we're asked for which values of these variables will the matrices be singular. To solve these problems, I'll consider row reduction. For Roman numeral 1, I'll first imagine dividing row 1 by A to produce this matrix. I like to have a 1 in that top pivot. Well, likewise, it would also be convenient to divide row 2 by C. 1 B over A, 1 D over C. The reason for this is now I can quickly take row 2 and subtract row 1 in order to create this matrix. Okay, I'm not completely in row-reduced echelon form, but I see everything that I need to see in order to answer the question. If this entry right down here, D over C minus B over A, were equal to 0, then I would have a row of zeros and a singular matrix. And so it will be singular if D over C minus B over A equals 0, which is equivalent to saying that B over A equals D over C, which is actually equivalent to saying it's going to be singular whenever I've got a proportion between the rows. A is to B as C is to D. And of course, the way proportions work, that also means when A is to C as B is to D. So the columns are in proportion. And that's pretty clear. If I have a matrix like 1, 2, 3, 6, that's a singular matrix because I can wipe out row 2 by multiplying row 1 by 3. What about a 3 by 3 matrix? Here, I want to know for which value of H will the matrix be singular. And so I'll use row reduction again. This time, I'll take row 2 and subtract 2 row 1s so that I can get a 0 in this position. I'll also take row 3 and subtract 1 row 1, so I get a 0 in that position. In effect, I'm making that 1 a true pivot. I don't even need to complete the row reduction to know what to do next. I see that I have a minus 2 here and an H plus 1 here. If it were true that H plus 1 was equal to negative 2, that those two entries were exactly the same, that would mean row 2 and row 3 were exactly the same. So whenever H equals negative 3, this matrix in Roman numeral 2 will end up being singular. That's it for this video. I hope you're starting to see that as we switch from thinking about equations and variables and unknowns to matrices, we're not only going to make things more efficient for ourselves, we're also going to gain a deeper understanding about what makes different types of equations have different numbers of solutions.